I've had a few questions this week already about independent events and using these formulas to check for independence. I did a search on YouTube for videos checking on independence, and I was really surprised that I could not find any existing videos that use these formulas to check for independence. So in this video, I'll give you a brief overview of what independent events are, how we can check for them, and then we'll run through a few examples. By definition, two events that are unrelated, in other words, the outcome of one event does not impact the outcome of the other event, are said to be independent events. So the opposite of independent events would be dependent events or related events. Essentially, what we're looking for is whether or not events A and B are somehow related to one another. So, for example, we did a survey last semester in this course where Stat 200 students were asked for their biological sex, male or female, and then they were asked whether they would prefer to drink beer or wine. We wanted to know if biological sex and alcoholic beverage preference were related. Turns out they are related. Females tend to prefer wine and males tend to prefer beer. So in that case, biological sex and alcoholic beverage preference are not independent events. We have three formulas that we can use when we have probabilities available to determine if they are mathematically independent events. If any one of these formulas is true, then all of them are true, and events A and B are independent. If you plug the values that you have into these formulas and any one of them is false, then all three will be false, and events A and B are not independent events. I think some of the confusion that I've seen this week is related to the use of the term event. This week is a special case in that all of the variables that you're going to be looking at when you're checking for independence are going to be dichotomous variables. In other words, there's two options. So for biological sex, male or female. In your lab assignment, you'll see cat ownership. There's only two answers, yes or no. In the previous example, last semester, alcoholic beverage preference was measured as wine or beer. Only two options. So technically, in that scenario, alcoholic beverage preference would be the variable, and then there are two possible events, beer or wine. If a variable is dichotomous, like the ones that we're going to be looking at this week, you'll get the same results whether you're testing for the independence between being female and liking wine, being male and liking wine, being female and liking beer, and so on. The results of all of those comparisons are going to be exactly the same because being female is the complement of being male, and in that scenario, preferring wine is the complement of preferring beer. Let's move ahead now and look at a few examples. So in this example, we're given the probability of A is 0.50. The probability of event B is 0.60, and the probability of A and B is 0.40. In this particular case, it's easiest if we use the first equation up here because we're given all of these values. So the probability of A times the probability of event B, in this case, is 0.50 times 0.60, which equals 0.30. 0.30 does not equal 0.40. So this statement is false. Remember, if one of these statements is false, they're all going to be false. These events are not independent. Let's look at another similar example. Here, the probability of A is 0.50, the probability of B is 0.80, and the probability of A and B is 0.40. Again, we'll use the first equation because we have all of these values already. The probability of A times the probability of B in this case equals 0.40, which equals 0.40, which is also the probability of A and B, which means that this is true. And if one of these is true, they're all true, which means that A and B are independent. In this scenario, we have one sample of adults, 30% like dark chocolate. In terms of gender in that sample, 80% were men and 20% were women. If gender and liking dark chocolate are independent, what proportion of women in this sample would you expect to like dark chocolate? So we're going to call event A liking dark chocolate. Event B, because the question is specifically asking about what proportion of women, we'll call event B women. So what we're given here is that 30% of everyone likes dark chocolate, so the probability of A is 0.30. Probability of B, or the probability of being a woman, is 20%, so P of B equals 0.20. And we want to know if A and B are independent, what is the probability of liking dark chocolate given that you're a woman? So sometimes the most difficult part of these questions is turning the scenario into an equation that we can use. So we want to know what proportion of women in this sample would you expect to like dark chocolate? So that would translate to, given that you're a woman, what's the probability that you would like dark chocolate? Or what is the probability that you would like dark chocolate given that you're a woman? Well, if these are independent events, then the probability of A given B would equal the probability of A, which is 0.30. Another way to look at this problem is that if gender and liking dark chocolate are independent events, then it doesn't matter if you're a man or a woman. The probability that you'll like dark chocolate is always going to be 30%. This is the last example that we're going to look at this week. This might be most similar to the example that you'll see in the lab assignment this week because you're given a contingency table. This is a contingency table from earlier in this week's lesson notes. We have biological sex here, females and males, and academic level, undergraduate and graduate. And we want to know if biological sex and academic level are independent. This is a special case because it's a 2x2 contingency table. So it's an example where we have two categorical variables that are both dichotomous. So both variables only have two levels. There are a few different ways that we could set up this example to test whether biological sex and academic level are independent. Because this example is phrased as female given undergraduate, we'll call event A being female and event B being undergraduate. Note, however, that you would get the exact same results if you would call event A being male or event B being graduate, because male and female are complements, undergraduate and graduate are complements. Your end result would be exactly the same, and I think that's where some of you are getting tripped up this week. This only works when the variable is dichotomous, so when there's only two levels. If there's three or more levels, which you're not going to see this week, you might see at the end of the course, I think it's a lesson 11 where we'll do chi-square tests, then it would matter. But if you're just looking at a 2x2 table, you could look at females or you could look at males. If being female and undergraduate are independent events, then male and undergraduate, female graduate, male graduate, they would all be the same. But in this particular case, we're looking at the events of being female and being undergraduate. We could look at any three of the formulas that we have up here because we're not really starting off with any calculations. The last few examples we've looked at use the first equation, so let's do something a little bit different. We'll use the second one. So if A and B are independent, then the probability of A given B, or in this case, the probability of being female, given that we know you're an undergraduate student, should be the same as the probability of being female. So the probability of being female, given that we know you're an undergraduate student. So we know you're an undergrad. If we know you're an undergrad, what is the probability that you are female? That'd be 38.14 over 72.42, which equals 0.527. So that is our P of A given B. Now we need to see if that value is equal to the probability of A, which is the probability of being female. We'll erase this. The probability of being female is going to be 6,027 out of 12,242, which equals 0.492. That is our P of A. So P of A and P of A given B are not equal. So that statement is false. If that statement is false, then all of the other statements need to be false. And these events are not independent.